Hi guys, today we're going to do a lesson on equilibrium graphs. And basically what we're going to do is we're going to talk about equilibrium and how it is represented in a graph. And hopefully by the end of today's lesson you will be happy like this guy here. Well, maybe not look like him, but at least be as happy as he is. Mr. Cooney?
Yes.
What does the word equilibrium mean to you?
Equilibrium and balance.
A balance of what?
Balance in general.
Just balance of anything?
Yeah.
Balance of number of students you put in my grade 11 class?
Yes.
When I think of equilibrium, I think of mental stability.
Kramer.
In our department.
Kramer and Cooney.
What about the science department? Do we have equilibrium?
Are we talking to you personally or just in general?
Yeah, me. Alright, so Mr. Walker was about to say that I have lots of equilibrium and I'm not crazy in any way, shape, or form. So, if we're actually talking about real chemical equilibria, although there's a lot of ways to tell if a system's at equilibrium. For this example here, the N2O4 is a liquid and the NO2 is a gas. And the liquid can be seen in this vial here. It's actually at the very bottom here, but you can't see it because of this, the cold steam or whatever you want to call it, the vapor that's around it. And when it's a gas, it looks like this, and it's got that nice orange-brown color to it, so you can see the gas really nicely. So you can see the reactants and you can see the products. And because you can see these macroscopic changes, you can tell when a system's at equilibrium because you don't see that change in color. Now, this isn't, you can't say, okay, this system's at equilibrium, or this system's at equilibrium, or this system's at equilibrium by looking at it like this, because equilibrium is dynamic. But if you were looking at the vial and it was like this, and it continued to be like this for a long time based on the conditions that it was at, then you could say that that's at equilibrium. So there's lots of different kinds of equilibrium depending on the conditions you have. So this is the one we're going to use for now. And we're going to take a couple, we're going to look at graphing this. So if you graph the rate of reaction against time for that reaction on the last page, you'll see that the rates of reaction at equilibrium, they are the same once that system comes to equilibrium. You'll notice that this is the rate of reaction of the reactants, or the forward reaction, and this is the rate of reaction of the reverse reaction. The rate of reaction of the forward reaction is very fast at the beginning and then levels off. The rate of the reverse reaction starts at 0 and increases until it levels off. And that's because when you have lots of reactants, you have a higher concentration of reactants, therefore you have a faster rate. When you have no products, or small amounts of products, you have a slow rate of reaction. So that's what this particular graph is telling you. Now this graph is very different than the last one. This isn't rate versus time, this is concentration versus time. And these graphs here are when you take, or when you start this equilibrium with lots of reactants and no products. So as the reaction goes, all of those reactants are made into products and their concentration decreases until equilibrium hits and you have a nice level off. Products generally start at 0, and as you let the reaction go, products are formed from reactants until you hit equilibrium and the concentration remains the same at a plateau. It doesn't mean that NO2 isn't being turned into N2O4, N2O4 isn't being turned into NO2. What it means is you don't see a change in the concentration. There's no fluctuation in that property. Now here's a different reaction. This reaction is when you take H2 and you mix it with N2 and you have NH3 being made. And we're not going to forget to balance this. Now in this particular reaction here, you have high concentration of H2, high concentration of N2 to start, and no product ammonia. And look at the concentration values that you have during equilibrium. Now, over here, you start with 0 reactants and lots of products, and if you compare these concentrations to these concentrations, you will notice that they are the same. In other words, equilibrium can be reached from either direction. In other words, you can start with products or you can start with reactants. It doesn't matter. You'll always achieve the same equilibrium. So that's it for today's lesson, or for this lesson anyways. I hope you enjoyed it, and I'll see you in class on not Monday, not Tuesday, but on Wednesday.